All right, let's connect some dots. We're going to go from a cosmic tilt, something that happened way out in space, all the way down to the maps we use every single day. And you're going to see how a massive collision billions of years ago is pretty much the reason you're even thinking about a summer vacation. Let's dive in. So it really all boils down to this one simple question. Why is it that when you're thinking about hitting the beach, someone on the other side of the world is strapping on their skis? How does that work? Well, the answer, it's not what you think. It has nothing to do with how far we are from the sun. It's all about geometry. Okay, so here's how we're going to tackle this. First, we're going to get to the bottom of why we have seasons. Then we'll look at the world's invisible grid, the one we made up to find our way around. After that, we'll sail through Earth's watery highways. And finally, we'll take a tour of the incredible landmarks that make up our planet. All right, part one, why we have seasons. And the whole story, it doesn't even start here on the ground. It starts with how our planet is moving and grooving through space. So our planet is basically doing two things at once, all the time. First, it's spinning on its axis like a top. That's called rotation. That 24-hour spin is what gives us day and night. At the same time, it's making a huge trip around the sun. That's revolution. And that 365-day journey is what we call a year. Simple enough, right? But there's a secret third ingredient here that makes all the difference. And here it is, the secret ingredient, our planet's axial tilt. See, Earth isn't spinning straight up and down. Nope, it's got this permanent lean, about 23.4 degrees. And why? Well, the best theory we have is that about 4.5 billion years ago, something absolutely massive, maybe the size of Mars, just slammed into our young planet and knocked it sideways. Seriously, that one cosmic crash is the real reason for the season. So just picture this. As the Earth makes its year-long journey around the sun, that tilt never changes. It's always pointing in the same direction out in space. This means for part of the year, the northern hemisphere is physically tilted towards the sun. The sunlight hits it more directly, like a flashlight shining straight on a spot. That's summer. And at the exact same time, the southern hemisphere is tilted away, getting that same sunlight at a slant, spreading it out. And that, right there, is their winter. This whole tilted orbit gives us 4 key checkpoints in the year. You've got the solstices in June and December. That's when our tilt is at its maximum point, either towards or away from the sun, giving us the longest and shortest days of the year. Then you have the equinoxes in March and September. These are like the perfect in-between moments where the tilt isn't favoring either hemisphere. So day and night are pretty much equal everywhere on the planet. 12 hours of day, 12 hours of night. And at the poles, this tilt creates something absolutely wild. Think about it. During the summer solstice, if you go way up north, above the Arctic Circle, the Earth is tilted so much towards the sun that the sun just never sets. It just circles the horizon for 24 straight hours. It's called the midnight sun, and it's a direct result of that cosmic lean. Okay, so this is the part where we bust a huge myth. A lot of people think seasons happen because we get closer or farther from the sun. That is completely wrong. In fact, get this. The Earth is actually closest to the sun in January, right in the middle of winter for the northern hemisphere, and we're farthest away in July during the summer. So one more time for the people in the back, it is all about the tilt, not the distance. All right, on to part 2, the world's invisible grid. Okay, so we've got this tilted, spinning rock hurtling through space. How in the world do we find a specific spot on it, or even agree on what time it is? Well, we came up with a pretty clever solution. We just drew an imaginary grid all over it. This grid is made up of 2 types of lines. You've got your lines of latitude. Think of them as horizontal rings around the Earth. They tell you how far north or south you are, which is a huge clue to what the climate is like. Then you have lines of longitude, which run vertically from the North Pole all the way down to the South Pole. And these lines, these are all about time. And the math behind time zones is just so neat. The Earth spins a full circle, that's 360 degrees, every 24 hours. If you just do the division, that works out to exactly 15 degrees of spin for every single hour. That simple equation, 15 degrees equals 1 hour, is the backbone of our entire global time system. Now, this is where the grid system gets really trippy. Let's talk about the international date line. It's basically the 180-degree longitude line, on the exact opposite side of the planet from Greenwich, England. And here's the fun part. If you cross that line heading east, say flying from Japan to California, you literally go back in time. Poof, Sunday becomes Saturday again. You get to live the same day twice. And if you go the other way, from east to west, you lose a day. It's wild. Okay, let's move on. Part 3 is all about Earth's watery ways. We're going to shift from the invisible lines we drew on the planet to the most obvious feature on its surface, all that water. So we've broken up the one big global ocean into 5 main ones. You've got the Pacific, which is just an absolute monster. It covers a third of the entire globe. And then on the other end of the scale, you have the Arctic Ocean, the smallest and shallowest, mostly covered in ice at the very top of the world. And branching off from these big oceans are what we call marginal seas. You know them, the Mediterranean, the South China Sea, the Caribbean. They're basically extensions of the oceans, and even though they're smaller, they are absolutely critical. They're hotspots for trade, for natural resources, and, let's be honest, for a lot of political drama. And then you have the really narrow bits, the natural waterways called straits. Look at these spots on the map, like the Strait of Hormuz or the Strait of Malacca. These are what we call strategic choke points. A staggering amount of global shipping, we're talking oil, cars, electronics, everything, has to squeeze through these tiny little passages. That makes them unbelievably important for the world economy. All right, time for our final section, landmarks of our planet. Let's zoom right into the big landmasses where we all live. So here they are, the 7 continents. You've got Asia, the biggest by far, home to Mount Everest, all the way down to the smallest Australia, which is so unique it's a continent and a country at the same time. Each one of these places has its own incredible features. And crisscrossing these continents, you have these huge mountain ranges. They're like the spines of the continents. Just look at the Andes, running down the entire west coast of South America, or the Rockies in North America, and of course, the Himalayas in Asia. But, not all mountains are created equal. We can actually group mountains by how old they are. On one hand, you have young mountains, like the Himalayas. They're still actively being pushed up by the collision of tectonic plates. That's why they're so sharp, jagged, and tall. On the other hand, you have old mountains, like the Appalachians in the eastern U.S. They're ancient. They've been worn down by wind and rain for hundreds of millions of years, which is why they're so much more rounded and gentle. And of course, we can't forget the world's great deserts. From the iconic Sahara in Africa to the cold Gobi Desert in Asia, these huge, dry regions aren't just random. They're shaped directly by the global climate patterns and the giant mountain ranges we just talked about. They're another massive piece of the planetary puzzle. So there you have it. We went from a cosmic accident that tilted our planet and gave us seasons to the invisible lines we drew to make sense of it all. We sailed the oceans and climbed the mountains. All of these forces work together to shape the world map as we know it. Which leaves you with one big question, right? What forces are going to shape the map of the future?